Hello everybody, this is TSA Zindabad and today we are going to discuss the daily challenge of Leetcode, which is out of boundary paths. So there is an M into N grid with a ball. The ball is initially at the position start row, start column. You are allowed to move the ball to one of the four adjacent cells in the grid, possibly out of the grid, crossing the grid boundary. You can apply at most max move to move the ball, and these are the given inputs, and we have to take a modulo because we might get an answer which is very big. Okay, so basically after reading this problem statement, I understand that I will be given something like a 2D matrix, right? And I will be given a specific row and a column value, right? The start row and start column value. So supposedly I was somewhere here, right? So if you look at this matrix, that is 1 comma 1 is my starting row index and this is my column index. So I need to tell the number of ways, that is the number of paths to move this ball, that I am supposing that here on this 1 1 index there is a ball present. So I need to tell the number of paths such that it goes out of the boundary. So out of the boundary means out of this 2D matrix of 3 cross 3 that has been given to me. That means it should either go here, then go here, or from here. Now it escapes out. It did escape out here. If it moves here, it escapes out. From here, if it moves, it escapes out. At any given position, that means in any given position of the cell, that is, if it is I and J, you can move only in 4 directions, right? So when you talk about the 4 directions, that is, you can either go up, you can go down, or you can go left or right. So these are the different positions you can go in. Another very important thing that you have to take care of, that you can apply at most max moves. What does this mean? This means that you can take, at most. So at most means it should be less than or equal to max move. So for example, let us suppose I had something like a 2. That means I can move 2 steps. So if I am standing at I comma j position, I have to basically find the number of paths so that I go out of the boundary, maintaining this condition, and I can only go in these 4 directions. I hope the problem statement is clear. Now let's jump into the approach. So when we talk about the approach, let's take an example so that we can visualize and then form an approach. Suppose we had a 2 cross 2 matrix, right? So herein the ball was initially present on 0, 0 index, right? So initial the start row is given to me as 0 and the start column is also given to me as 0. So my ball is here. I need to tell the number of paths this ball can take so that it goes out of boundary, right? While considering 2 things. The first thing being that I can take at most the max move steps from that particular position I am present on. And the second thing is that for each cell index ij, right, I can either move in the 4 directions, that is up, down, left and right. Okay, so how will I do this? I understand that whenever we talk about number of paths, I want to understand what all possibilities I have, right? What all possibilities I have to go out of boundary. So whenever we talk about possibilities, we try exploring all the paths, right? So when we talk about exploring all paths, we know what we have to use. We use recursion. So what does recursion say? It says that you figure out the base case, you just handle one case, I'll handle the rest. So when I am standing, for example, here in this example, that my I is 0, j is 0, right? For me to go out of bound, either I can go up. If I go up, my index will reduce by 1, right? And my column remains the same. So as my index is less than 0, so I see that it has gone out of the boundary. So whatever is my answer, I can simply increment it. For example, it was 0, now it becomes 1, right? And let us suppose for this example, the max move were given to me as 2. So as you see, I'm just moving one step, right? And we can have 2 here, which is depicting max move, right? So as I've moved one step, the remaining steps that I have is 1. So this is feasible. That means this is doable because it is leading me to my final answer. This is one way of doing it. The other is if I would have went left. So what happens here is if I go left, then my row remains as it is. So this was what was given to me initially, right? So I'll have 0 as it is for the row, but now my column is decrementing to -1. So now as j is less than 0, right? So again, my answer would be incremented. Why? Because my max move was initially 2 when I was standing on I comma j. Now I'm going to left. So 2 minus 1 will give me 1 move, right? So this makes my answer 2. The other thing that I can do is I can say that I'll go to the right. But now when I go to the right, what happens is when you go to the right, you were initially at 0, comma 0. So you will have something like 0, comma 1. Now, if you see none of them, neither I nor j, they're not going out of the boundary. So that means, and while I've moved this, I have decremented my max move by 1 because I've moved one step, right? From this cell, I have moved to this cell, right? So I've taken one step, but I still have one step remaining. So from here, now when I'm standing here, I can figure out for its above, that means for up, down, left, and right. So that I can figure out the number of paths, right? So that means through this, my ball will traverse over different indexes on the matrix, and I need to figure out for which all cases is it going out of the boundary. I hope this is clear. It's a very basic recursion question. And further, the optimization will be done, right? So let's understand and write its code, and then we'll talk about its time and space complexity, and we'll also have a quick dry run of how things are happening and is there a need to optimize and how to. Okay, so this is the question that I have, right? What I can do is I can simply have something like I'll make a solve function, right? So let's quickly make an int solve function. Now, basically what this function will be having is we'll pass almost the same parameters here, right? Let's just make this I mean, I'm just making it for my own purpose. You can let the name be as it is, right? Now, what I want this solve function to be the recursive function was actually getting me the answer, right? So when we ever write recursion, we break down it into 3 parts. That is the base case. Second is explore all the possibilities. And the third thing is write the recursive function. So let's keep some space for the base case, right? As we know, we have to find all the paths. So that means whatever we are figuring out, we have to sum it up. And then we have something like a recursive function. So herein, I see that for any index ij, I can move in 4 different directions. So I can say that first I can go up and call a recursive function. So that will be solve mn. Max move will decrement by 1 because if I am going up, I am moving by one step. My index I, that is the row, gets decremented by 1. J remains as it is, right? This is the first direction. Then what I can do is I can have for down. Here and what happens is my max move will decrement by 1. Now, when I'm going down, my row gets incremented, right? Imagine a matrix and draw these indexes so that you are always clear how is it happening. The other direction I can go in is left, right? So when you have to go to left, the row remains the same, the column decrements by 1, and the last one is right. And herein I'll have a solve function that is mn max move -1. My row remains as it is. My j, that is the column, increases by 1, right? So these are the different recursive calls for any one particular cell that I will be making. Okay. Now after this, what happens is I know at the end, I need to return the sum of all of these, right? So I can have something like return up plus down, down plus left plus right. And as here it is mentioned that we might need to take a modulo because the answer might be very big. So you can have something like a long mod and initialize it with 1e9 plus 7. And here I am taking a mod. Okay. Now let's talk about the base case. See, whenever I talk about base case, I want you to guys to understand that base case will have the termination point for the recursive call, as well as it will also have the edge cases. So basically for this problem, I want to find the number of paths that are leading me to a point where I am outside this grid's boundary. So if you see that will be the base case, right? So that will occur if I becomes less than 0 or my j becomes less than 0, as we saw when I was trying to form the approach, right? Or it can occur that if my I becomes greater than equal to m, or j becomes greater than equal to n. In that case, I'll say that you have to return a 1. Why? Because you have moved to the next place, and when you have moved to the next place, you have moved outside the boundary. So return a 1. And the other thing that I need to check is, see, as we're decrementing max move every time, right? So supposedly you kept decrementing, moving in the grid, and you have yet not found, you have yet not achieved a basic position where you're outside the grid boundary, right? But your max move, that means the given steps for you have become 0 or less than 0. So in that case, what you will do is you will say return a 0, because see, it is not possible. If you do not have any steps to go forward to, you have to return a 0, right? And now let's quickly pass here the parameters. So this is max move, and we have the start row and start column. I think we are good to go. Let's quickly run it once. Okay, it's taking a lot of time because it's a recursive code. Okay, so we got a time limit exceeded, but just for the purpose that what we've done is right, let's take a smaller example. The first one that has been given. I hope this should run with recursion. And yeah, here it's running because it is a smaller test case. So I understand that the approach that I've formed is right, but for bigger test cases, I will get a TLE. So now let's discuss this code, have a dry run, and then talk about optimizing it. Okay, so this was the code that we just wrote, right? So let's consider this example that we initially were talking about, that we have a 2 cross 2 matrix and my ball is here on 0, 0, and I have something like max move, which is initially 2. So first, while we are having this dry run, I will be creating the recursion stack space as well as the recursion tree for you to understand how things are happening. So when you see here, what happens is the first solve call is made, right? The start row and start column both are 0, 0, and the max move that I have is equals to 2, right? So here in my recursion stack space, similar function is pushed inside it and my pointer is pointing towards it. So now when we come to the solve function, it checks that is either of these cases being satisfied. So it says no, the base case is not being satisfied. Even the max move less than equal to 0 condition is also not being satisfied because max move right now is greater than 0. So it will say now you will be catering these 4 conditions, right? So for just one index that is 0, 0, I'll have 4 different calls. So my first call is made, that is for up. Here I say solve, my max move gets decremented, so it becomes 1. My I is decremented, so it becomes, see, I here was 0, so it becomes -1, j remains as it is, right? So now this function is called and it is pushed in the recursion stack space. Now my pointer will point to this function. As soon as I am on this function, I see that my base case is being satisfied. Why? Because I is less than 0. So for this, I will return a, okay, just a minute. So it is being satisfied. So as the base case is being satisfied, so I will return a 1 to my parent function, right? And this will pop out from the stack. And now I am again, my pointer is pointing towards the first base function that we had added, and we have completed the up for it, right? Now we'll go to down. So next call is made for down. Here my move gets decremented by 1. Initially my move was 2. So for that, I'll have move minus 1 that makes it 1. Then I have I plus 1. So I initially that what I had was 0. So it becomes 1 and j remains as it is. So this call is added into my recursion stack space and now my pointer will be pointing here, right? So when I am on this function, I see that my base case is not being satisfied and my max move are still greater than 0. So now for this cell, I need to figure out these 4 conditions again, right? So what I'll say is, I'll say, okay, for you, we'll have an up, right? So when we have an up, we call the solve function. We decrement the I value, which is in this case 1. So it becomes 0. J remains as it is. And now my max move becomes 0, right? So this function is added into the recursion stack space. And now my pointer is pointing here. When it comes here, the base case is not satisfied, but the edge case is satisfied, which says that if the max move is less than or equal to 0, that means return 0. This means that though you have exhausted all the moves or the steps you had, but you have still not got the answer. So you simply return your parent a 0. As it returns it, it gets deleted or popped out from the stack. And I am again standing on its parent function, that is S1 0, 1. Now it will go to its down. It will make a call for down. So it will say we have to decrement the move, it becomes 0, right? The value of I, which was 1, gets incremented to 2 and j remains as it is. Now this call is added, so S2 0, 0. Now my pointer is pointing towards it, right? So here we see that this array had a size of 2 cross 2. That means my m and n are 2 and 2. And here the base case is being satisfied because my I is equal to m and m was 2. So I will return a 1 in this case for this function. Then this gets popped out. Then another call is made, that is left. So when the left call is made, what happens is it will say decrement the move. The I remains as it is, that means 1. And now my j gets decremented by 1. So it makes it minus 1. So this call is added, that is 1 minus 1 0. My pointer is pointing towards this call. And here, as you can see, j has become less than 0. So it will also return a 1 because in all these conditions, we are getting the answer. Why? Because within the given steps, I have reached outside the boundary, right? Now for this, again, this will get popped out because it has lived its life. So now I am again on the function S1 0, 1. So here a right call will be made. Now herein it says whatever is the value of I, let it be. J becomes plus 1. So that is 1, 1 and move gets decremented to 0. Now when this function is added, that is 1, 1, 0. My pointer is pointing here. The base case is not satisfied because 1, 1 index lies within the grid. But as you see, I have exhausted my steps. So I have to return a 0. So now I can see that for my, this gets popped out. So I can see for S101, I'll get an answer as 2 because I'll be summing it all up, right? So I have got this answer for this. That means it has completed its lifetime. It gets popped out and it returns its answer to its parent, which was S002. Now my pointer is again pointing to this function. It says you have explored the up down Now you have to explore the left. So for the purpose of exploring the left, it says make the call, right? We decrement the move, move becomes 1, right? I will remain as it is, I remains 0. Now what happens is j becomes -1. As j becomes -1, it was initially 0, it becomes -1. So 0, -1, 1. This function call, I'll make here the other stack so that it does not get cluttered. So now my pointer will have I mean, see, all of these are exhausted, only this was pending, so I'll write this here, right? And the one we have now, I'll write it here. So S0 -1 1, and my pointer is pointing here. The base condition satisfies because j is less than 0, it will return a 1, right? So after that, it will go to the right. For right, it will say have a solve function, right? Wherein I remains the same, so that means I is 0, j becomes +1, that is 1, and the move becomes 1. So now you see we have S0 1 1, and my pointer is pointing towards it. 0 1, that means I and j are within the boundary, and I still have a max move. So for even this cell, I'll be computing 4 different values, right? That will be up, down, left, and right, right? I hope that this is clear how the dry run is happening and how finally we are attaining the answer, right? That means we'll get some answer from here as well, and then we'll sum it all up and we'll return the answer to this function and we'll have the answer, right? But when you look at this, we understand that as we have 4 different choices for every index, right? If it is not satisfying the base condition or the edge condition, so I have 4 raised to the power n as a time complexity, which is exponential. It is super huge and will lead to time limit exceeded error. And the space complexity in worst case scenario is O of n because of recursion stack space. As you saw, we are maintaining, right? So in the worst case, you can have a space complexity that is O of n. Now I need to optimize this. So when I talk about optimizing it, right, we need to understand that optimization means boiling down the time complexity, right? So I can use something like dynamic programming. Why I can use it? I can use it because the above problem has overlapping subproblems. Now, what is overlapping subproblems? I'll highlight them. See, here I called for a function, right? It might be recalled in this tree diagram because I did not completely draw it, but there might be conditions where the same function call is made all over and over, right? So when that happens, we get sub problems which are overlapping in nature, right? So in that case, whenever you have overlapping subproblems, you can apply something like dynamic programming, right? So now what does DP says? It says that once you've computed something, store it, then use it from here. Do not recompute. So basically it helps boiling down the time complexity from exponential to somewhat, you can say it can be O of n, O of n squared, or O of n cube, entirely depending upon what is the problem statement, right? For this problem statement, we'll understand what will be the time complexity, but this is a generic thing that it boils down to a huge extent. Now, for applying DP to the above code, so this was the code that we had. I'll quickly copy paste it so that we have a clear screen. Okay, so this was the code that we had written for the purpose of recursion. Now I want to convert it into dynamic programming. So basically in DP, what happens is you have two methods. You can either go for memoization, right? Or you can go for tabulation. So basically what is memoization? Memoization is a top-down approach, right? Wherein you start building from the nth case and then go downwards, and tabulation is bottom up. That means you start from the base case and then you move upwards. What I generally follow is I solve it using memoization, and for the purpose of further decreasing the time and space complexity, I convert it into tabulation and everything, right? So it entirely depends upon you how you want to do it. So right now, let's work with memoization. So the first thing that we need to do is we need to initialize and declare a DP vector. So if you look at the constraints for this problem, you will see that the value of I, J, that means the indexes that are given to us. That means the start row, start column, and the max moves. All of these will always be less than equal to 50. So I can have something like a 3D matrix wherein I'll initialize all of this to something greater than 50. Like just like you can have something like 55, 75, whatever suits you, right? And then you can apply DP here. Now, very basic question that some of you might have is, why are we making a 3D DP? See, why do we have this 3D DP? Entirely depends upon that. See, solve is your recursive function. So the size or the dimension of your DP depends upon number of parameters which are changing, right? So if you see in the solve function, you can say that in the recursion call, the value of I, the value of C, here the value of J, max move, in all of it, right? These are constantly changing. So that is why it becomes a 3D DP vector. And I do not have to do anything new. I'll just simply add a if condition. I'll add DP here, right? I'll save DP of this particular row, column, and the number of moves that you have left. If that has been pre-computed somehow, right? I did a recursion call, I got an answer, and it is stored in the DP. You'll return it, right? You return that value rather than recomputing all of it here. And whenever you are computing something finally, you will be storing it in the present row, column, and number of steps, that is max moves that you have. This is the subtle change that will make. After making this change, the time complexity will boil down to something O of M into N into max moves. So if you see these all of these are somewhat like less than 50, right? And similarly, the space complexity is also the same. So we have boiled down the time complexity, which was exponential, to somewhat, which is O of M into N into max moves, and where M, N, and max moves are at max 50, right? So now let's quickly code this up and see if it is working fine. So this was the recursive code that we just wrote, right? So we can have simply like int dp 55, 55, 55, right? And I can have something like a memset function. It like resets the dp. So I'll say initialize it with -1 and size of dp, right? Then here I'll add an if condition. I'll say if dp of I, j, max moves is not equal to -1, in that case you return me dp of I, j, and max moves. And the other thing I'll say is here, when you're computing all of it, right, you'll store it in dp of ij max moves. I think we're good to go, right? The other thing that you can do is that you might still get a TLE, right? So whatever is the value of the up, you can even take a mod with that. In case you are, even after doing memoization, if you are getting a TLE, right? So just to be safe, I'll be adding it here. I think we're good to go. Let's run it once. Okay. Okay, there is not an S. I'm sorry. There is a typo. There is no S. So even here, I need to delete it. Yeah, I think we're good to go now. Hmm. Max move. Okay, I'm sorry. These little typos. And let's submit it. So we're getting the right answer. Let's quickly have a dry run and understand how are we getting these answers now. Okay, so this was the DP memoization code that we just wrote, right? Now, I'll be taking an example and we'll have a quick dry run so that we understand how DP is useful, right? And for even larger examples, how it adds on, right? So suppose you have a 1 into 3 matrix. So that means there's just one row and there are three columns. You have something like this, right? And here the ball is present on the index 0, comma 1. So that means the ball is present here. Now I need, and the max move that is given to me is 3. That means you have 3 maximum steps for you to go outside the boundary, right? So what happens is here the recursive function is called, right? So you say that initially you had something like 3 moves and you were on 0, comma 1, right? So these are the steps. This is I and this is J. So from here, you will come here, you will see that the base case is not being satisfied and the max move is also not being satisfied, right? Because it is greater than it. See, though I have to create a DP of 55, I cannot create that big. So I'll just create it of minimal size so that you guys understand how it's working, right? Just consider that here you have something like 54 and even here you have something like 54 from 0, 1, 2, 0, 1, 2, right? And as it is 3D in nature, right, it is really hard for me to, have that capacity to draw it. You need to just visualize it and understand, right? So basically what happens is I'll quickly erase this. We can basically store it in blocks for you to understand. That will be better, I personally feel, right? So basically, this first call is made, right? As soon as this first call is made, what happens is it checks for the base condition, max move, none of it satisfied. We'll check that is it computed? We'll say no. We'll say okay, then go for its up. When you go for the up, move gets decremented by 1. I becomes -1, J becomes, now here when you see that J will remain as it is, so it remains the same. Now for this function, as you see that the base case is being satisfied, so it is returning a 1 to its parent, then it will go for down. When it goes for down, my step gets decremented, it becomes 2, right? Because it was 3, so it becomes 2. My I is incremented, it becomes 1, J remains as it is. So as you come here, you see that the moves are not less than and the base case is also not being satisfied. So in this case, you will have further 4 function calls for down, right? So you will have an up. So when you have the up call for this function, you will decrement the step by 1 and I becomes 0, J remains the same. So here as the base case is not being satisfied and we still have the max move. So we have to now figure out 4 choices for this, right? So when you have to figure out 4 choices for this, you will have something like an up here. So in the case of up, now you'll have solve. Now move will become 0 and your I will be decremented to -1 and J remains as it is. It will return a 1 because of the base condition. Next, for down, the moves will be 0, right? And my I will get incremented, so it becomes 1. J remains as it is, right? So now for even this, I need to figure out 4 different conditions. And every time anything is computed, it is being stored in something like DP, I, J, and the max move. And whenever it is required, it is directly being taken rather than recomputing all of these steps. So that is why we are getting a time complexity that is O of n into m into the max moves that have been given to us. And this is the space complexity also. I hope this is clear, right? this will be a very big tree structure. So for that purpose, I have not completed it. But if you have any doubts, you can always comment in the comment section and we can discuss it. Thank you so much for watching the video till the end. Please like, share, and subscribe.